Vera, you mentioned that the subject of the fractional parts of the N-alpha sequence are related to dynamical systems, to ergodic theory. Could you say a few words about the connections?
I was always excited when I realized that between two fields which seem to be completely far from each other and for completely different methods and everything, it turns out that there is a strong interaction. And this is what I can say about N-alpha sequences and dynamical systems and ergodic theory, and even more, or to prove. So when I started to work on graph theory and discrete mathematics, I would say also combinatorial number theory, then I did much less. I will not say that I left, but I did much less on Diophantine approximation. A few times I turned back, and this was always, I think, by an occasion when somebody asked me or a problem on Diophantine approximation or on N-alpha sequences, where the problem came from dynamical systems and ergodic theory. The first time was when Dorothy Maharam and Arthur Stone asked a problem on, in some sense, a characterization of alpha by a sequence of integers, not by the continued fractions, but by a sequence of integers for which you get with which you get a very good approximation for alpha. And the characterization of these three. On that problem, we did work with András Bíró and Deshoulier, and so I have maybe one or two papers. This was maybe 15 years ago or so. Another occasion was when Sinai, also, as we know in dynamical systems and ergodic theory, asked a problem, simultaneous Diophantine approximation. What he asked, it is a question about a phenomenon which could be similar what we have for N-alpha sequences. And we answered this question with Szekes. And the third time I met or realized this strong connection of Diophantine approximation and physics is the story of quasicrystals. It is really a very admirable and wonderful story in the history of physics and in the history of mathematics. So Shechtman, who is a physicist in Haifa, in '82, he is a material physicist, and he investigated the atomic structure of different materials. And as we all learned in school, I think at least I learned it, but everybody learned in school, that the atomic structure you have two different forms, either crystalline, so a very periodic one, or amorph, which means a very random-like one.
Amorphous, yes.
And he did find something which is between the two. And these are called now quasicrystals. And he realized that phenomenon when he investigated the atomic structure of aluminum and magnesium.
Alloy.
The alloy of magnesium and aluminum. And using electronic microscope, where one gets a so-called diffraction pattern, which shows somehow the atomic structure, he got some extremely interesting results. This showed something which could indicate that it is a crystal, because it showed a lot of periodicity or similar properties. But at the same time, it showed some five-fold symmetry. And since we know that in the space there is no
crystals cannot have five-fold symmetry.
Crystals can't have, so which is a mathematical fact actually. It was neither a crystal nor an amorph structure. And it showed an extremely interesting similarity with the Penrose tiling, where, as we know, Penrose tiling is a tiling of the plane which is not periodic, but periodic from almost periodic, or now we say it is quasi-periodic, which means that it has a lot of different properties what periodic system has. And what is behind in that similarity? But it was quite clear that there must be. And now how is it related to fractional part and alpha sequences? Now I would say shortly that a fractional part and alpha sequence is nothing else but a one-dimensional Penrose tiling. Namely, the brain proved that how you can generate a Penrose tiling. You take the five-dimensional space and you take a proper strip and lattice points between those 2 points and project it on a proper way to a plane, and then you get exactly one of the Penrose tilings depending how you choose the planes. Which means this shows already that from the lattice, which is a periodic one, how you get this quasi-periodic one. And now how to get the fractional part and alpha sequence. You do exactly the same. You take the two-dimensional lattice, you take a proper strip, you project it to a line or to another line, and you get either the integer part or the fractional part of an alpha sequence. So you get, and this shows in some sense that why we can say that a fractional part and alpha sequence is a quasi-periodic one. Not only because the three-distance theorem, because the three-distance theorem is one thing, but actually if one has the three-distance theorem, what now many people proved it, but I proved it and used it, it is not just that it has the three-distance property, but it has a lot of periodic-like properties.